Hello everyone, welcome back. In this video, we are going to talk about the Arrhenius equation and activation energy. Okay, so in the last video, we ended with this equation of the Arrhenius equation. And this is one form where we have the rate constant K is equal to A. Remember that A is this what we call the pre-exponential factor. This is the term that pulls together things really involving that Boltzmann distribution, the mass, the probability of collision, the steric factor involved with causing reactions to happen. And then we have this exponential term where EA is the activation energy. And then we have our good friend, the ideal gas constant times temperature. So this is probably not the form of the Arrhenius equation that you've worked with before. So let's work to turn it into the form that you are more familiar with. To do that, we first take the natural log of both sides. And then if I do some algebra and apply my log rules, I can come up with this form of the Arrhenius. And this is what we would call the linearized form. And what we mean by that is if we were to make a graph of the rate constant versus temperature, what we would find is we would find something that has an exponential shape. When we take the natural log, we get something that becomes, now, if we graph the natural log of K versus 1 over T, we now have something that is a line. And this linearized form is a lot easier to work with experimentally. So the reason we use the Arrhenius equation is really this activation energy. So finding this activation energy is able to really tell us things about this transition state, and it's going to tell us how much more energy the transition state has than the reactants. And it can also give us the energy relative to the products, because remember that the difference between the delta E, that's an E, the delta E between the reactants and products, this is a state function. And so we can express that as the delta G of the reaction or the delta H of the reaction, depending upon what we're holding constant. So in this, we can, with knowing the activation energy, we can get a full picture of the energetics of the reaction and to begin to understand some of the energetics of the mechanism for this reaction. So why do we like to linearize? It turns out that experimentally it makes things easier, because what we have is on the y-axis is we have this natural log of K, and on the x-axis we have 1 over T. And so that means that when we fit this data, we get a fit in the form of y equals mx plus b. And so our slope is going to be equal to minus EA over R, and our intercept is going to be equal to the natural log of A. Now, when we work with this linearized data, we have to remember that our slope and our intercept have units. Our slope is defined as the change in y over the change in x. And so that means that the units of slope are going to be the units of my y-axis divided by the units of my x-axis. And so in this case, for this graph, my slope is going to have units of Kelvin, because the natural log of k is going to be unitless, and 1 over t is going to have units of 1 over Kelvin. And so that means that this intercept is going to have the units of the y-axis because it's the y-intercept, it's the y value. And so in this case, it is going to be unitless. Now, this A, this pre-exponential factor, this is an experimentally determined property. And you can assume that it is relatively temperature independent. It's not exactly true, but for most cases, it's a pretty decent approximation. Now, if you are looking for values for A, there are tables of common reactions listed in your textbook that provide you with both the activation energy and the pre-exponential factor for those reactions.